Farisa here. Today I want to share with you about mathematical logic. My friend, Hannah, will share with you the meaning of it. So, what is mathematical logic?
Hey there. My name is Hannah. So, you want to know the meaning of mathematical logic, right? Everyone would have the difficulties to understand the meaning of this topic well. We must go through all the chapter to understand what mathematical logic is. But well, according to Merriam-Webster Dictionary, mathematical logic, also known as symbolic logic, is a science of developing and representing logical principles by means of a formalized system consisting of primitive symbols, combinations of these symbols, axioms, and rules of inference. Complicated, right? Relax, we can understand this if we know what is the basic concept of mathematical logic. The basic of mathematical logic are propositional logic and logical connectives. So, what is propositional logic? Proposition is simply the statement, which in this case is mathematical statement that has a truth value. It is either true or false. Statement are sentences that declare something, which means questions or instructions are not a statement, as they cannot be given a truth value. For example, February has 30 days. 4 plus 2 equals to 3 times 2. The first sentence is false, but it is a statement. The second sentence absolutely is a statement, as it also has a truth value which is true. Next, stop the bus. Have you done it? Both of these sentences are not a statement, as they are instruction and question. So, what is logical connectives? We can build more complicated, molecular statements out of simpler ones using logical connectives. For example, this is a molecular statement. Telephone numbers in the USA have 10 digits, and 42 is a perfect square. The two shorter statements are connected by an and. We will consider 5 connectives. And, Sam is a man and Chris is a woman, or, Sam is a man or Chris is a woman. If then, if Sam is a man, then Chris is a woman. If and only if, Sam is a man. If and only if Chris is a woman, and not, Sam is not a man. So to analyze logical connectives, it is enough to consider propositional variables, sometimes called sentential variables, usually capital letters in the middle of the alphabet, P, Q, R, S and others. These are variables that can take on one of two values, T or F. We also have symbols for the logical connectives, and, or, if then, if and only if, not. This means P and Q, called a conjunction. This means P or Q, called a disjunction. This means if P then Q, called an implication or conditional. This means P if and only if Q, called a biconditional. This means not P, called a negation. I think all of you have understand what mathematical logic is.
Oh, I get it, but may I ask something? Is formulas such as in mathematical formula, is also a statement?
Oh. In math, formula is also a statement whose truth value may depend on the values of some variables. It would be nice to use variables in our mathematical sentences. For example, suppose we wanted to claim that if n is prime, then n plus 7 is not prime. This looks like an implication. I would like to write something like if p, n, then not p, n plus 7, where p, n, means n is prime. But this is not quite right. For one thing, because this sentence has a free variable, that is, a variable that we have not specified anything about, it is not a statement. Now, if we plug in a specific value for n, we do get a statement. In fact, it turns out that no matter what value we plug in for n, we get a true implication. What we really want to say is that for all values of n, if n is prime, then n plus 7 is not. We need to quantify the variable. Although there are many types of quantifiers in English, for example, many, few, most, etc. In mathematics we, for the most part, stick to two, existential and universal. The existential quantifier is this and is read there exists, or there is. For example, there exists x where x smaller than 0 asserts that there is a number less than 0. The universal quantifier is this and is read for all or every. For example, every x where x bigger and equal to 0 asserts that every number is greater than or equal to 0. These quantifiers express the scope of the predicate over the subject term, which is why they are called as predicate logic.
Oh, now I understand what mathematical logic is. Okay then, thanks Hannah, for sharing with us. After hearing what Hannah explained, I'm still wondering how can we determine the truth value of each conditions. I think I can ask Nicole about this.
Hi, I am Nicole. That's easy, Farisa. The truth value of a statement is determined by the truth values of its parts, depending on the connectives, which means P and Q is true when both P and Q are true. P or Q is true when P or Q or both are true. If P then Q is true when P is false or Q is true or both. P if and only if Q is true when P and Q are both true, or both false. Not P is true when P is false. This can be easily shown by constructing the truth tables. The truth table compares different combinations of conditions to see what truth values they give. It shows the mechanics of logic. The simplest truth table is the negation. A negation simply reverses the truth values of the statement that is our input. So, if our input is true, the negation is false, and vice versa. Next is conjunction. A conjunction claims that two statements are true. If either or both statements are false, then the outcome will be false. For this truth table, there are 4 possible outcomes. This will be easier if we use a real situation. Take these 2 simple statements as example. Today is Wednesday. I have a scout meeting. So, we want to know if P and Q is true. In other words, today is Wednesday, and I have a meeting is true. We need to think through the 4 different situations that might happen here. 1. P is true, and Q is true. If we know 2 true inputs, then we know that P and Q is true. So it is Wednesday and I do have a meeting. 2. P is true, and Q is false. Now we do not have 2 true statements, so the outcome of P and Q is going to be false. So it is Wednesday but I do not have a meeting. 3. P is false and Q is true. In the reverse situation we still get a false outcome to P and Q. So it is not Wednesday but I do have a meeting. 4. P and Q are both false. In this situation neither simple statement is true, so the conjunction is obviously false. It is not Wednesday and I do not have a meeting. The third one is disjunction. A logical disjunction, also called an inclusive OR, claims that at least one of 2 statements is true. An exclusive disjunction, or exclusive OR, claims that only one of 2 statements are true. Let's look at the truth tables again. This truth table shows that output for both inclusive and exclusive disjunction. From the truth tables, we can see that the first output for each disjunction is different when P and Q are both true, while other 3 output are same between each disjunction. Now, with any logical expression, we can decode the truth conditions of different cases. The conditional PQ represents an if-then type of compound statement. In a conditional the if clause is the antecedent, which means the condition, and the then clause is the consequent, which means the outcome. For example, if you pass the exam, you will pass the course. You pass the exam represent by P, which is the antecedent, while you pass the course represent by Q, which is consequent. So, how does this work? There are 4 cases for this conditional PQ. 1. P is true, and Q is true. If I told you the conditional PQ and you pass the course, then I did not lie to you, so the output of PQ is true. 2. P is true, and Q is false. If I told you the conditional PQ and you passed the exam but you failed the course, then I lied to you, so the output of PQ is false. 3. P is false, and Q is true. If I told you the conditional PQ and you failed the exam but you passed the course, then I have not lied to you. My statement did not rule out an alternative way for you to pass. So, the output of PQ is true. 4. P and Q are both false. If I told you conditional PQ and you failed the exam and failed the course, then I still have not lied to you. My statement only referred to what happens in the case that you pass the exam. So, the output is true. So, how about by conditional PQ? The biconditional PQ is a conjunction of reversed conditionals, conditional PQ and conditional QP. So, the biconditional will be false when P is false, and Q is true. Otherwise, the same reasoning applies as with the conditional truth table. In this case, when both conditional PQ and conditional QP are true, we say that P and Q are equivalent. This logical equivalence can lead us to a tautology. We can also create equivalent statements in other ways, such as with De Morgan's law. A tautology is a compound statement which always results in truth value. It doesn't matter what the individual part consists of, the result in tautology is always true. The opposite of tautology is contradiction. A contradiction is always false no matter what the truth values of the input statements.
Wow, thanks to both of you. I also want to share with you the application of mathematical logic. From my research, I found that mathematical logic widely used in computer science field which include the logic gates. Logic gates apply to Boolean algebra with the truth values denoted as binary, 1 or 0. It is used to analyze and simplify digital circuits. It is also called as binary algebra or logical algebra. It has been fundamental in the development of digital electronics, and is provided for in all modern programming languages. Let me show you a video for us to understand more about logic gates.
Let's remember this legendary mathematician first. A son of a shoemaker from England played a vital role in converting logic into mathematical form with his passion and love for mathematics, logic and philosophy of mathematics, George Boole. He was born on 2nd November 1815 in England. He is best known for his books, The Mathematical Analysis of Logic 1847 and The Laws of Thought 1854, which contains Boolean algebra. Regular algebra works on numbers, and its basic operations are addition, subtraction, multiplication and division. But Boolean algebra works on Boolean variables true and false. The basic Boolean operations are and, or and not. Boolean logic is the foundation of the information age. Unfortunately, George Boole died on 8th December 1864 in Ireland at the age of 49, walking a distance of 3 miles in a heavy rain from his home to the university for the dedication and love for teaching, and lectured wearing his wet clothes. But what is a logic gate? Before a logic gate, let's see what a simple gate is. A gate can allow or block people based on whether it is open or closed. In the same way, a logic gate can allow or block output current based on whether input currents are high or low. And these are called logic gates because they allow output based on a logic applied on the inputs. Note that number of inputs can be 1 or more, but number of outputs can only be 1. In computer terminology, high current or high voltage, which is on, is called as 1 or true, and low current or low voltage, which is off, is called as 0 or false. We have 3 basic logic gates, and they are and, or and not. AND gate, it allows output current be high only when all the input currents are high. Output of one gate is low if at least one input is low. Let's see the simple 2-input AND gate. When we connect 2 relays in series as shown, then it behaves as AND gate and allows output current be high only when both the inputs are high, otherwise it outputs low. OR gate. It allows output current be high if at least one of the input currents are high. It makes output current be low when all the input currents are low. When we connect 2 relays in parallel as shown, then it behaves as OR gate and allows output current be high if at least one input is high. Otherwise it outputs low. NOT gate. It just flips the input and gives the output. It makes output current high when the input current is low and makes output current low when the input current is high. NOT gate is just a normally closed relay, and its output is just the negation of input.
Here is some example of problem involving the Boolean algebra and logic gates. The nation of Upper Slobovia has gained a missile defense capability governed by its Security Council. The council consists of 4 members: the U.S. Upper Slobovian President and 3 councillors, the Chiefs of Staff of the Army and Air Force plus the President's Uncle Homer. The missile system is to be activated by a device obeying these rules. Each member of the Security Council has a button to push. The missiles fire only if the President and at least one councillor push their buttons. Design the rocket firing circuitry. So, for the solution, the first step is we specify the input and output variables in the two states of each. For the input, letter P represent President's button, where 1 is for pushed and 0 is for not pushed, while letter X, Y, Z represent the councillor's buttons, where 1 is for pushed and 0 is for not pushed buttons. For the output, letter F represents the fire missile's command, where 1 is fire and 0 is don't fire. Next, we need to construct the truth table listing all possibilities. From the truth table, we can observe that, if the President and at least one councillor agree, the output is firing the missiles. While if only the President pushed his button, the output state does not fire the missiles. And if the President did not push his button, then do not fire. From the truth table, we can write a Boolean expression like this. To simplify the formula, we can construct a map that shows 3 groups of 4 ones each, giving this expression px plus pi plus pz, or px plus y plus z. So, the rocket firing circuitry can be designed as followed.
Another calculation can be done by using this logic. The scenario is, Snidley's automated cafeteria orders a machine to dispense coffee, tea, and milk. Design the machine so that it has a button input line for each choice and so that a customer can have at most one of the 3 choices. Diagram the circuit to ensure that the at most one condition is met. So, how to solve this problem? First, we specify the input and output variables in the 2 states of each. The input consists of letter C represent coffee button, 1 for pushed, 0 for not pushed, letter T represent tea button where 1 for pushed, 0 for not pushed, and letter M represent milk button, 1 for pushed, 0 for not pushed. The output represented by letter X equals choice verifier where 1 is for acceptable input deliver the choice selected and 0 is for unacceptable input light and error light. For the second step, we construct the truth table giving the output desired for each input. We have to note that X is 1 when exactly one of C, T, and M is 1. So, the circuit can be designed as followed. For discussion we have discussed before we're focusing on Boolean logic, which is binary logic that only have 2 variables, either true or false, 1 or 0. But, there is another form of logic which is an extension of the binary logic where there can be multi-value logic also called as degrees of truth. The extension surfaced as there are some problem that cannot be solved using the crisp logic. As we talk about fuzzy logic is a logical system which is an extension and generalization of classical multi-valued logics. Fuzzy logic attempts to use the principles of logic on situations which are too complex to be seen in simple yes or no terms. The term fuzzy means things which are not very clear or vague. In real life, we may come across a situation where we can't decide whether the statement is true or false. At that time, fuzzy logic offers very valuable flexibility for reasoning. We can also consider the uncertainties of any situation. Fuzzy logic allows for answers between 0 and 1. For example, 0.1, 0.2, 0.3, etc. that represent the human thoughts such as definitely small, pretty small, sort of small, not very small, and not at all small. A typical application is the use of fuzzy logic principle to automatic washing machines. According to official website of Samsung, one of the big company of manufacturer, the fuzzy logic in a washing machines checks for the extent of dirt and grease, the amount of soap and water to add, direction of spin, and so on. The machine rebalances washing load to ensure correct spinning. Else, it reduces spinning speed if an imbalance is detected. Even distribution of washing load reduces spinning noise. Neurofuzzy logic incorporates optical sensors to sense the dirt in water and a fabric sensor to detect the type of fabric and accordingly adjust wash cycle. In simple words, the input of the fuzzy control system is the quantum of dirt and its rate of change and also the weight of clothes. With these three inputs, the quantity of washing powder, water quantity, water flow rate, washing time, rinsing time, and spinning time are the outputs. I think that's all for today. This explanation of mathematical logic only covered some fundamentals such as the meaning of mathematical logic, the basic concept applied in this topic, and some application and calculation involving this knowledge. Note that mathematical logic is a very wide field and developing from time to time.